Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 92, a channel and a plate are welded together as shown to form a section that is symmetrical with respect to the y-axis. Determine the moments of inertia of the combined section with respect to its centroidal x and y axis. So here is the given figure. So let's have the properties of channel 8 by 11.5. This is provided before this problem. So for our solution, let's have the table, and this is channel 8 by 11.5. The area is 3.35, depth, width of the flange, and so on and so forth. So the orientation is also here. So for the channel section, this is the centroid. Take note the orientation is this is the supposedly y-axis in this orientation. And therefore, the y-axis for the channel is the x-axis for this orientation. And the distance of the centroid from the outer edge of the flange is barred x in this orientation, and it is 0.572 as shown. Then area, call this yg, and we can compute that by Varignon's theorem or first moment of mass principle. Then the depth of or the width of the flange, this one, which is this, is 2.26 inches as shown in the figure. So area is area of the flange plus area of the plate. So area is 3.37 plus 12 times 0.5. In other words, the area of the plate is 6 square inches. So 3.37, which is this, the area of channel 8 by 11.5. So area therefore is 9.37 square inches. Then apply first moment of mass or Varignon's theorem. 9.37 times yg equals 3.37 times 0.572 plus 6 square inches times the distance to that edge is half of 0.5, 0.25 plus 2.26. So 6 times 0.25 plus 2.26. Yg therefore is equal to 1.813 inches. Having found Yg, we now compute I bar x, and it is equal to this axis of the channel is Iy, and Iy is 1.31. So let's transfer the moment of inertia of the channel to this axis here. So Ix or I bar x or Igx is 1.31 plus 3.37, then distance Yg minus 0.572 square. So that's the distance between these 2 points through this axis, centroidal axis. Then for the plate, the moment of inertia is 12 times 0.5 cube over 12. Then area 6, and this distance is quantity 0.25 plus 2.26 minus yg, then quantity square. So plus 12 times 0.5 cube over 12 plus area 6 times quantity 0.25 plus 2.26 minus yg, 1.813 quantity square. So the value of the first term is equal to 6.500. The second term, this one, where the plate 3.040. Therefore, Igx is equal to 9.540 inches to the fourth. Likewise, for Iy or Igy, for the channel, it is just Ix because this is the x-axis. You look at the orientation, Ix plus I bar x of the plate, which is equal to 12 cube times 0.5 over 12. So Igy is equal to Ix of I bar x of the channel 32.5, then plus 12 cubed times 0.5 over 12. So IGY is equal to 104.5 inches to the fourth. Level 93, two angles 76 by 76 by 6.4 mm angles are welded to a channel 250 by 22.8 channel. Determine the moments of inertia of the combined section with respect to centroidal axis respectively and perpendicular to the web of the channel. So here is the given figure, and the properties of the angles and the channel are incorporated in this problem. So here they are, the properties of the channel and the angles. So by symmetry, the centroid lies on the centroidal y-axis as shown, and this is the centroid of the entire area. And for the channel, the centroid is expected to be below. So this is our reference should be the junction between the angles and the channel. So here, and for the location of the centroid of channel, it is barred X below the edge, below this reference axis. So this is 16.1 as shown mm, 16.1 mm. So that's barred X for the channel. And for the angles centroid, since legs are equal, then distance from this edge and from the bottom edge of the angles also equal to barred X, which is equal to barred Y, 21.2 as shown in the figure. So the distance of the centroid of the angle or each angle from the y-axis is simply half of the depth of the channel, 254 over 2 minus 21.24. For the moment of inertia later, when we transfer the moment of inertia of the angle centroidal y-axis to that y-axis, centroidal y-axis of the entire area. So for our solution, let's compute the area first. The area is area of channel to 890 plus 2 times area of angles 929. So to 890 plus 2 times 929, area equals 4748 mm squared. Then by Varignon's theorem to solve for YG, again, this is our reference, this horizontal line. So area of channel, we treat 16.1 as negative because it is below this axis here. So 4748 YG equals 2890 times negative 16.1 plus 2 times 929, then positive 21.2. So YG therefore is equal to negative 1.504 mm. So it is below this horizontal reference line. So this is really G, and that's YG, which is negative 1.504 mm or 1.504 mm below this reference horizontal axis, which is the junction between the two sections. Then IGX is equal to, for the channel, this axis here through the centroid is not the x-axis because of that orientation, it's the IYY, and IYY is 0.949 times 10 to the 6. Then we transfer it here. This distance is equal to 16.1 minus 1.504 because they lie on the same side of this reference axis. They are both below. So the distance is 16.1 minus this distance, which is 1.504. So therefore, for the channel, IGX equals IY of the channel 0.949945 times 10 to the 6 plus area to 890, quantity 16.1 minus 1.504 square. Then for the two angles, it is IGX of the angle 2 times IGX or IXX of the angle, which is 0.512 times 10 to the 6 plus area 929 times distance. So the distance square is 21.2 plus yg. So the distance between the centroid of the angle and this centroidal axis here of the entire section is 21.2 plus 1.504, then quantity square. So plus 2 times quantity 0.512 times 10 to the 6 plus 929 times quantity 21.2 plus 1.504 square. So IGX is equal to 3.542 times 10 to the 6 mm to the fourth. Likewise, for IY or IGY, it is IX of the channel, 28 times 10 to the 6. Remember, this axis here, which is perpendicular to the edge, it's perpendicular to the edge is IXX. So that is 28 times 10 to the 6 IGY, then plus 2 times quantity IY of that angle, which is the same, 2 times 0.512 times 10 to the 6 plus area 929 times distance is depth of the channel divided by 2, 254 divided by 2, then minus 21.2. So again, this distance is half the depth of the channel. The depth of the channel is 254, so 254 over 2 minus 21.2. So that distance there, quantity square. So computing IGY equals 49.82 times 10 to the 6 mm to the 4th. Level 94, two steel plates are welded to a rolled W section as indicated. Knowing that the centroidal moments of inertia, I bar x and I bar y are equal, so determine part A, the distance A, B, the moments of inertia with respect to the centroidal x and y axis. So here is the given figure. Since we can compute I bar x independent of A, then we begin by answering part B first. Take note that I bar x equals I bar y um, as the condition in this problem. So I bar x is simply Ix of this W 14 by 38, whose properties are provided, plus we need to transfer the moment of inertia of this plate, which is equal to centroidal moment of inertia, 26 times 1 cube over 12, plus area, which is 26, 26 times 1, then distance square. This distance is half of 0.5, half of 1 inch, 0.5, plus half the depth of this W 14 by 38, so 14.1 divided by 2. That's the distance between the centroidal x-axis and the centroid of this plate, rectangular plate, then quantity times 2. So for the solution, area is area of the channel 11.2 plus 2 times area of the rectangular plate 26 times 1. So area is 63.2 square inches. Then I bar x or IGX is again IX of the channel. So call that XG, by the way. So I bar x is 385 for the I bar x of the W section, W14 by 38, plus 2 times quantity moment of inertia of this rectangular plate with respect to the centroidal axis is 26 times 1 cube over 12. So 2 times quantity 26 times 1 cube over 12 plus its area, which is 26. And again, the distance from the centroid to the centroidal x-axis is half of 1.5 plus half of the depth of the W 14 by 38, which is 14.1. So 14.1 over 2 plus 0.5 quantity square. So I bar x is equal to I bar y equals 3353 inches to the fourth. Then in the second part, we need to express xg in terms of A by the principal first moment of mass. So the area total is 63.2. So this is our reference axis. So 63.2 times xg equals 11.2 area of the wild plants times 0, because that's the reference, plus 2 times 26 times this distance is a minus this distance is a. So 2 times 26 times a. So 63.2 times xg, this is our reference, total area times xg equals area of the W 14 by 38, 11.2. Then because this is the reference, so that's 0, plus 2 times 26 times distance of the centroid of the two rectangular plates from here is a. So therefore xg in terms of a is equal to 65 over 79a. Then we transfer the moment of inertia of each section here by parallel axis theorem. And remember, the value of the moment of inertia with respect to this centroidal y-axis is 3353 point something, 0.46, I think. We'll use the exact and accurate value in computing for A. So moment of inertia of the wide flange section IYY 26.7 plus its area xg square. So 3353.46, which is I bar y, which is I bar x, is 26.7 plus area 11.2 times distance xg quantity square, and xg is 65 over 79a quantity square. Then we transfer the moment of inertia of this rectangular plate. So 2 times moment of inertia with respect to this axis is 26 cubed times 1 over 12 plus area 26, and this distance square is a minus xg quantity square. So 2 times 26 cubed times 1 over 12 plus 26 times a minus xg 65 over 79 a quantity square. Simplifying, so again this is the value here when we copy the excess value of 0.46. So 353.46 equals 26.7 plus 7.5821 a square plus 8788 over 3 times 2. So that's the value. Then this value here, 2 times 26 times this value square, is 1.6331 a square. Combining like terms, 29807 over 75 equals 9.2152 a square. So finally, we can now solve for a. A is equal to 6.567 inches.